In this part, we're going to talk about Jacobian. Jacobian is a mapping of differential changes in one space to another. So, in short, is that we try to find out what is my position change based on tiny differences of the parameters. The parameter can be an angle, can be a position of some kind of linkage. Then overall, those changes is going to affect the position in space. So let's start from a function which include two variables, r equals to f q1, q2. So if we want to find out r dot, this one is differentiate in terms of time. You might say, okay, I just dr dt. Yes, that's correct. But this time we are not trying to deal with dt only. We want to try to find out what is the change if my q1 and q2 have tiny change. So what we're going to do is using partial differential equation, partial f, partial q, but over here, we're going to do partial q1, partial t. That's for the change for the first variable q1. And since we are having two variables in this function, so the second one is doing the same thing. We are partial q, sorry, this one is q2, partial f, partial q2, and this one is partial q2, partial t. So in short, what we're trying to do is partial f, partial q1. This part over here is in terms of t. So we are having q1 dot plus qf partial q2 multiplied by q2 dot. So you can see that instead of differentiate everything in terms of time directly, we are differentiate in individual parameters and multiply by the changing rate of individual ones. Then we can find out what is my changing rate for the overall position in space. That is something we're going to do. And furthermore, this one over here can be further processed into this format. Partial f, partial q1, partial f, partial q2 as a components of in 1/2 matrix. And over here, we're going to have q1 dot and q2 dot. So if you see something like this, it means that we can combine those two matrices together to find out what is my my position change in space. What's the benefit of this one is if we do have another component, we need to come up with the position. This one might be in terms of x, and we also need to find the position in terms of y. So y has another function, which is still a function of q1 and q2. Then we can follow the same procedure. So it means that this one over here is single output. If S is another output of function, let's say this time I have G, Q1, and Q2. Then I can do the same analysis, which is S dot equals to partial G, partial Q1, Q1 dot plus partial G, partial Q2, Q2 dot. And we can have the same process over here, partial G, partial Q1, partial G, partial Q2, Q1 dot, Q2 dot. Okay, you might notice that there are some similarities between those two representations. They both has the same input, Q1 dot and Q2 dot. And the format of the components over here, they are the same, which means if we try to put both of them together, we can actually do that by putting R dot S dot together. I'll write it down over here by putting R dot S dot over here. Then I'll have the 4 components from here, 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 and here. Then the variable becomes Q1 dot and Q2 dot. This matrix over here, including all 4 partial differential terms, this is my Jacobian matrix. That's how we define that. Okay. So since we are dealing with robotic device, which means when we try to describe something moving in robotic system, we are having 6 components. They are velocities in 3 directions, angular velocities in 3 directions. So when we are writing down everything like that, our velocity vector is a combination of 6 components. They are Vx, Vy, Vz, omega x, omega y, and omega z, related to individual components. And in order to find out the change in terms of velocity, we need to have a Jacobian matrix multiplied by all the inputs. The inputs over here we might have multiple variables because we might have multiple joints. Individual joints has their own angle, has their own distance. So combining everything all together, we can find out what is my velocity and angular velocity. That's the basic idea. Okay. So when we are doing something like this, we actually can do 2 directions. One is forward calculation. The other one is inverse calculation. What do I mean? Because when we have a robotic system, we know we need to come up with a lot of transformation metrics. And use those transformation metrics, we can actually find out the position in the end of a robot based on individual parameters like theta, A, D, and alpha. So those are going to be the input information over here. The output is going to be the velocity in terms of x, y, z, psi, theta, and phi. So what we're going to have is we have our v vector equals to v omega. Then we have Jacobian in terms of q. Q1 dot, Q2 dot, depending on how many you have, you're going to have corresponding number of variables. That is one way. So now, if we do know our velocity, the 6 components, in that case, if we desire to find out what is the condition of individual joints, can we do that? The answer is yes, because this one over here is a matrix or a conversion matrix from one side to from Q to the velocity side. So if we try to find out those things, we actually using this matrix inverse to find out the same information. Of course, there are some restrictions over here. We're going to talk about those kind of things later. But basic idea is, yes, we can convert the position from the change of input parameters. We can also find out the change of parameters based on my current velocities in the end of a robotic device. That is how we deal with those kind of things and interchange the information between both sides. So this is basically what I'm talking about earlier. So if we know all those kind of change, we can use Jacobian matrix to convert them from each other. Basic idea is something like this. We just use the conversion and we try to find out the conversion matrix using forward kinematics. Those are the procedures that we actually come up with all those components. You might take a look and understand the procedures or how to derive those coefficients from one end to the other. Keep in mind when you are doing something like this, we are doing partial differential equations instead of direct differentiation. We're going to have an example later, but if you are having something like x equals to cosine theta 1 plus sine theta 2 plus tangent theta 3, something like this, then in order to find out x dot, you will need to differentiate. This one is going to be my function theta 1, theta 2, theta 3. So when you have those three variables, you need to partial differentiate one individually and put that into the components of this matrix. There is one tricky part over here. You might expect the Jacobian matrix is a square matrix. Actually, most of the time it's not going to be. So when you do not have a square matrix, you're not doing anything wrong. We're going to explain this one later and show you some technique how to convert from regular Jacobian matrix to its inverse. So this is also something we have for the how to convert everything from the differential equation into the Jacobian matrix. Keep in mind, normally we're going to have 6 columns over here because we have 6 outputs on this side. They are x dot, y dot, z dot, omega x, omega y, and omega z. Those are based on Euler coordinate system. So you will need to have 6 by n. And over here is the number of variables we have in our system. So that is how we do it. And this is just how we convert everything and their physical representation. Later on, we're going to talk about something which is a little bit different because we are having velocity and omega. And we know this one is going to be a big Jacobian matrix corresponding to Q1, Q2 dot, those kinds of things. But we can actually do something like B equals to JV and still have the same Q over here. And for the omega, it's going to be the same. But the J omega is going to be a lower part of the matrix. Then we still multiply by Q1 dot, Q2 dot, those kind of variables. Then when we synthesize the Jacobian matrix, it's going to be JV and J omega combined together. We're going to have more detail about this one later when we are dealing with 2 big examples in the end of this module. Okay, let's work on one example. This example over here is a 2-bar linkage. And we start from this O over here, and we try to find out the Jacobian related to x, y at this position. So should be pretty straightforward because the most important thing we need to find out is what is my current position. So when we are doing something like this, okay, so we will need to know the geometry distance over here. This one over here is, of course, L1 cosine theta 1. This one over here is L2 cosine theta 1 plus theta 2. For the y direction, this is L1 sine theta 1. This one over here is L2 sine theta 1 plus theta 2. Those are just based on geometric relationships. So the geometric configuration can actually give us x, y. We're talking about the position only because we haven't dealt with anything related to velocity. So we just try to write down the relationship from theta 1, theta 2 to x and y, which is the position over here. So clearly, over here in terms of x, I got L1 cosine theta 1 plus L2 cosine theta 1 plus theta 2. For y direction, it is going to be L1 sine theta 1 plus L2 sine theta 1 plus theta 2. Okay, should be pretty straightforward. Now we got our position and the relationship between xy position and theta 1 and theta 2. So the next thing we need to do is, okay, let's say I have this one as my r. Then I have r dot. That is going to be x dot, y dot, or try to find Jacobian for theta dot, theta 1 dot, theta 2 dot. Okay, this is just based on the definition of Jacobian matrix. So for the Jacobian matrix, what we need to do is to write down the partial differential terms over here. We talk about this one when we are dealing with the two variable ones. So we need to do partial differential, partial differentiate for the function of the first row and the derivation for the second row. So let's do that. So clearly, this one is going to be my h1. Let's name this one as h1 theta 1, theta 2. This one over here is going to be my h2, theta 1 and theta 2. Okay, so when we have those kind of things defined, what we're going to do is to find out partial h1, partial theta 1, partial h1, partial theta 2. For the second row over here is partial h2, partial theta 1, partial h2, partial theta 2. Okay, and we do have both h1 and h2 defined in this specific equation over here. Then the next thing we need to do is just partial differentiate. So we're going to have this one over here equals to negative L1. We deal with theta 1 first. So differentiate the first term becomes negative sine theta 1 multiplied by L1. And the second one, since it's cosine, so we need to have the negative sine 2 sine theta 1 plus theta 2. For the term over here, it's going to be the same. We are partial differentiated in terms of a theta 1. So I got L1 cosine theta 1 plus L2 cosine theta 1 plus theta 2. For the second column over here, I'm going to have negative L2 sine theta 1 plus theta 2. This one is going to be L2 cosine theta 1 plus theta 2. This is going to be my 4 components. We don't have this term for the components over here. That is because those two terms over here only have information related to theta 1. So when we partial differentiate that result, it should not be existing over here because they do not have anything to do with theta 2. So they must be 0. Okay, so this one over here is going to be my Jacobian matrix. Should be pretty straightforward. Now, we need to talk about something, singularity. What is singularity? Singularity means that you cannot derive the result. So when we say the Jacobian matrix is singular, it means that determinant of Jacobian equals to 0, or det jq equals to 0. Okay? When we say the determinant cannot be 0, it means that Jacobian matrix is not full rank. That means that this thing is singular. Okay, so this is just something that you might need to. It might be a good idea you remember those kind of definition in this module. So now what? What is the real deal over here? Okay, so when we have singular, it means that it becomes a straight line. So when this one is a straight line, it's singular because you cannot predict whether it's going to move in this direction or in this direction, since they are not full rank, or the determinant of your Jacobian equals to 0. To be precisely, if theta 2 equals to n pi, n equals to 0, 1, 2, then your Jacobian matrix is going to be singular, which means if you have your configuration like this, and like this, they are both singular. So that might be a special case when you are doing the calculation. It doesn't mean you cannot have this position. It only means when we are doing calculation, we're going to have some problem. Physically, it might be doable, but mathematically, your determinant becomes 0, so you might have some problem over here. Now, for the Jacobian matrix, as I mentioned earlier, in many cases, it's not going to be a straight matrix. So when it's not a square, what are we going to do? We cannot. The problem is we cannot inverse a non-square matrix directly. So we are not going to use like a -1 for this thing. We do not. Instead, we are doing something like this. We make it a square matrix. Then we start to do that. But keep in mind, it can be a little bit different depending on your M and N matrix. M and N. If your M is smaller than N, then use this formula. If you are having a square matrix, which is M equals to N, then you just use regular inverse method. But if your M is greater than N, then use this formula. So depending on what kind of case you have, you might use the pseudo-inverse formula accordingly. Then we should be able to inverse the Jacobian matrix and to whatever we need to be. Let's work on one example. So we want to find x for the Jacobian convention leads to this one. So this one over here is going to be my output. This one is actually the input. In the previous few slides, we used Q on this part. This one is going to be my velocity or anything like that as our output. So clearly, this one over here, m, the number of m is not equals to 2. M is actually smaller than n because this is 2, this is 3. So if we go back to a previous slide, we are going to use this formula. So the formula tells us it's going to be, let's do this one as a side. A plus equals to AT, AT inverse. So this is the formula that we're going to use. To do that, I have 1, 1, 0, negative 1, 2, 0. The transpose of this matrix is going to be 1, 2, 0, 1, 0, 2, 1, negative 1, and 0. If we multiply everything all together, this one over here is going to be 5, 1, 1, 2. This is my J. This is my J. JT equals to this one. So JT inverse is going to be 5, 1, 1, 2 inverse. So it is going to be 10 minus 1. This one multiplied by this one minus this one multiplied by this one. The formula is going to give us 2 and 5. We swap those two positions and put negative number in front of those two components. That is going to be my inverse matrix. So with this one, I have my inverse equals to 1 over 9, 2, negative 1, negative 1, 5. Okay, so this is this part. Now, in order to find out A plus or the inverse of my Jacobian matrix, I'll have to 1, 0, 2, 1, negative 1, 0. Transpose of Jacobian, like this one, multiplied by the inverse matrix. So when we do this, it becomes 1 over 9, 1, 1, 4, 4, negative 5, negative 2, which implies my x vector is going to be this matrix 1, 1, 4, 4, negative 5, and 2, multiplied by the output. So if we do this, it's going to be 1 over 9, negative 5, 13, and 16 over here. So when you do the inverse Jacobian, we can actually find out the input parameters are the components in this specific vector. And that is how we use inverse Jacobian to solve for this kind of problems. So this page talks more about Jacobian matrix. So if we want to inverse that, it's just like something what we want to do. If it's a full rank or it's a square matrix, we can just use inverse to do that. Depending on what kind of things, we might have different boundary singularities. Sometimes it's not non-invertible. So when it's non-invertible, we have two different kinds of boundary conditions. We have two different kinds of singularities. The first one is boundary singularities occur when the tool tip over here on the surface to the work envelope. So it might follow a specific trajectory, so we might need to worry about the boundary condition. Sometimes it's interior. So just like what we do earlier, when this one over here becomes this one, definitely is singular. That is interior singularity. Or if I have something like this, it goes back 180 degrees. Then this one is going to generate the singularity as well. So depending on what kind of singularity you're talking about, it has different kind of a configuration. When this configuration occurs, it's not going to be full rank, which means it's going to be singular. So when it's singular, you need to be careful to figure out what is the geometry configuration of the structure at this moment, because you might damage your system or you might overturn some of the joints and break the joints or break some sensor. So when you are having those kind of stuff, check the physical setup and ensure you are not going to damage anything before move on. So this one is talking more about singularities. So that is something you might want to take a look and understand what is bounded and what is the what cause singularities. That is something we're going to talk about for this part, the basic of the Jacobian. Next part, we're going to give you guys a few examples so you guys can have better understanding how to get those Jacobian metrics from transformation metrics. And once we come up with something in chapter 3 and chapter 4, and we want to find out velocity instead of just position, how are we going to use those transformation metrics to come up with the answers? That is going to be the next video.